Welcome back, team. We are dealing with lesson 13 today, which is the graphs of functions. And this one is mostly important because it sets up your knowledge of all the toolkit graphs that you're going to be using later on in all of your math classes. And so specifically knowing the names and the equations and then the general shape of each toolkit function is very valuable moving forward. That way when someone says the name, you know exactly what shape to be thinking of. Just like when I say circle, everyone can imagine a circle right away. Or if I say triangle, everyone can imagine a triangle right away. When I say exponential function, I need everyone to be able to imagine that shape that I just drew in blue. And it needs to be that simple where you just know, oh, exponential looks like that kind of half U shape I just drew. And if that makes no sense yet, don't worry, we're going to see all the toolkit functions. But that is the whole point of this lesson, really. We're going to talk about a little of domain and range and piecewise functions, but the main idea of this lesson is to get you to know the toolkit functions. All right, so that being said, the application we're going to do is going to deal with piecewise defined functions, which are functions that are multiple functions stitched together. And we're going to see what I mean by that in a few examples. But what we're building up to, it says when you go to a buffet, there are often 3 price points. Babies under 2 are usually free. Kids 12 and under might be $15, and adults might be $25. We want to write a piecewise defined function, P of A, that represents a price, P, of your meal based on your age, A. And then we'll graph this function. So you can see I already set up what the graph is roughly going to look like. That way we can just draw the lines on top of it later. So you might want to put the same looking image in your notes, where we're going to have a price is going to be our Y value, and an age is going to be our X value. And then I put the numbers from the problem. The 2 ages were 2 and 12. The 2 prices were 15 and 25. But we're going to leave it there for now, and then we'll come back to this at the end once we know what a piecewise defined function looks like. All right, so first, we just need to extend our knowledge of domain and range to graphs. Last lesson, we talked about how to look at domain and range from a set of points or from a table, but now we want to look at it from an actual graph, which in my opinion is actually easier. When we had a relation and we were listing the domain and range where we had a bunch of ordered pairs, you just look at the X values and list them, look at the Y values and list them. And it wasn't that was challenging, it's a little tedious to list every single X value and every single Y value. So usually what we do is we list them using an interval that describes which X and Y values we're actually looking at. So for number 1 here, it says find the domain and range of the function graphed below. The same definitions of domain and range are going to be used from what we had before. So we are going to say that big D represents the domain and big R represents the range. But then we're not going to list out every single X value because notice that as this graph goes along, yeah, you have the X value -3, -2, -1, 0, 1, and 2, but you also have every single conceivable X value in between those whole numbers. And you can't list out all those infinitely many decimals individually. So instead we say in a interval that represents all those numbers. So what we're going to do is we're going to look at the smallest X value and the biggest X value used. So if I look at the far left point, the X value getting used by that point is -3. And on the right side, we're using the X value of 2. So for my interval, I'm going to have -3 on the left and 2 on the right, where -3 is the smallest X value and 2 is the biggest X value. Then I have to check, though, if we're actually using the endpoints. So specifically looking at the left dot and the right dot. The left dot you can see in here is a filled in dot. Okay, so right there, that is filled in. The right dot, on the other hand, is an empty dot. Okay, so no fill. That is very important because a filled in dot means that point is there, but an empty dot with no fill means that point is not being used. So on the left side, because it's filled in, we use a bracket on the -3. And that bracket means that we are including the -3 in our interval. On the right side, where we have an open dot with no fill, we're going to use a parenthesis on that 2, because no fill means we don't actually include 2. We include everything up to 2, but not 2 itself. All right, so our domain is -3 to 2 with everything in between. Now for the range, we're going to look at the y values. So the lowest y value I see is down here on the left, and that y value is -5. The highest y value I see, be careful, it's not the right point. It's as high as this graph goes, which is all the way up here at +4. So the lowest number I saw was -5. The highest number I saw was 4. So I write my interval -5 to 4. And then now I got to think about, again, do I include all the points or not? So on the left side, again, it's a filled in dot, so we include -5. On the right side, or the top of this graph, it's a 4 with a line through it. When we draw a line that goes straight through like this, it represents every single one of these being closed dots along the way. So as long as there's not an actual open dot drawn there, like that, as long as there's not that, this line going through it represents there being a closed dot. We just don't draw all the little dots because there would be infinitely many of them. So because of that line going through 4, we include 4, which means it gets a bracket on the 4. All right, for number 2, we're going to do the same idea. We're going to set up our domain as big D and our range as big R. The smallest x value I use on this graph is the -1 on the left. And the biggest x value I use is the 3 on the right. So my domain goes from -1 to 3. But both of the dots on the left and on the right are empty dots. So I use parentheses on both sides, where the parentheses represent that that dot is not filled in. So -1 is not an answer and 3 is not an answer. But we use everything infinitely close to -1 and 3. So again, open dot, we put a parenthesis. For the range, the lowest y value I see is this -2 at the bottom, and the highest value I see is +1 at the top, where the lowest one, -2, and the highest one, 1, I list -2, 1. On the bottom of this graph, both of the dots are empty dots. So I have to check both of them, but since neither of them are filled in, I put a parenthesis on the -2. And at the top, again, because it's a line that goes through +1 for the y value, we count that line as a closed dot. Because again, we just don't put infinitely many closed dots like this along the way, because that defeats the purpose of drawing the line if we had to draw all the dots. But a line represents infinitely many closed dots, so we put a bracket on that one. All right, so now that we know what domain and range looks like, now we can introduce toolkit functions. So in real life, you will often hear things described as moving in a straight line or growing exponentially, linear growth, exponential growth. Like these are the 2 most common phrases we kind of get in financial terms in real life. And in order to understand what is meant by those phrases, we need to know the basic graphs that they refer to. So there are 9 graphs which you need to be able to draw rough sketches of from memory. So these are things you need to have down, just like a flashcard type of learning experience here. The shapes and domains of these graphs are going to be very important as we move forward. So number 3, I'm not actually going to answer. Number 3 is for you to pause right now and try to draw as many as you can before I show you what they all are, and just try to see what you can come up with. So you all know what a linear function is because we've talked about linear functions. We've drawn a bunch of straight lines, so you know one of them. But have you heard of a quadratic or a cubic or a rational function, any of these other 9 that we're about to name? So try to list out as many as you can, and then I'm going to show you in just a second. All right, hopefully you paused and tried. So now here we go, one at a time. So notice I already have them drawn and named, and then what we're going to be doing is writing the domain and range for each of these. Okay, so what you need to do is copy down the pictures I have, copy down the names and the equations, because what your homework is going to ask you to do is label these graphs. I'm going to show you something that looks like this on the homework, and I'm going to ask you to name it, write the equation, and give me the domain and range of it. So right now we have the pictures and the information. Later on, you're just going to have the picture, and you're going to have to work backwards. Okay, so the first one is called a constant function. Right now, I have the line y equals 3 drawn, but this 3 could be any number. So 3 is just an example number. but a constant function can be y equals anything, where the y value on this graph is 3, and it's always 3. For every point on that line, the y value is always 3. We've graphed horizontal lines before, so you guys have all seen constant functions. The domain of this is all real numbers, negative infinity to infinity, because it uses every x value from the left to the right. The range of this, though, is just the singular point 3 in this case, because the up and down doesn't get used. There's nothing above or below 3 being used. So again, we use everything from left to right, which is the domain is all real numbers, negative infinity to infinity, but we don't use any y values except for positive 3. Okay, a linear function we've seen plenty of. That's just a straight line. The basic one is y equals x, where it has a slope of 1 and a y-intercept of 0. This is the easiest one to remember domain and range for because it's everything. So the domain is negative infinity to infinity, and the range is also negative infinity to infinity. This graph goes all the way down and all the way up, and it also goes all the way to the left and all the way to the right. So it uses everything for both x and y values. A quadratic is a parabola, has the equation y equals x squared. When you hear quadratic, you should think of a parabola, which is this U shape. Okay, you'll learn more about quadratics at the end of this class, and then also a whole bunch of knowledge about quadratics in college algebra. But you need to hear quadratic and immediately think U shape. Okay, that's what should come to mind. The domain of a quadratic is all real numbers, negative infinity to infinity, because we can plug in any x value we want. The range, though, is 0 to infinity, where we include 0. That is the lowest point on the parabola. And then it goes all the way up, but it does not go down. Okay, so it starts at 0 and then goes up from there on both sides. So bracket on 0 all the way to positive infinity. All right, the next one is a cubic function. A cubic is called a cubic because it's x cubed as its formula. And I have never had a great way to describe this shape. I literally call this a squiggly. So I call a cubic graph an upward squiggly, but to be honest with you, when we're talking in mathematics, we just call it a cubic. So it's almost like if you don't know what a cubic is, it's hard to tell you what a cubic is, because this shape, like as mathematicians, we know this as a cubic shape, but if you're not going to say cubic, I literally call it a squiggly, because I've never thought of a better way to describe it. So realistically though, you should call it a cubic every time you want to think of this shape. But for the first time you learn it, I call it an upward squiggly. So now this uses all real numbers for both domain and range. You can use all x values and all y values because this graph goes all the way down, all the way up, and all the way to the left and all the way to the right. So it uses absolutely everything. Okay, next one is a square root graph. The square root of x represents the square root graph, and this looks like half of a sideways parabola. So a sideways parabola would be this full U shape, because remember, parabola and quadratic mean U shape. The square root function is only the top half of this. If we said negative square root of x, then it would be the bottom side. But the base square root function, y equals positive square root of x, is just this top half here. The domain of this graph, it starts at 0 and goes all the way to infinity. So it starts at 0 and then goes off to the right. And the range similarly starts at 0 and goes all the way up to infinity. So both the domain and range are 0 to infinity, because we use that point 0, 0, but then we go up and to the right. A cube root, okay, is the cube root of x. So what the cube root represents is if you have something like, say, 8 is equal to 2 cubed, then we would say that the cube root of 8 is equal to 2. So it's very similar to a square root. It's just a exponent of 3 instead of an exponent of 2. But we use cube roots fairly often because they make this sideways squiggly, which if you notice, looks very similar to the cubic function, just turned on its side. So there's a lot of connections between those two graphs. And the domain and range are both all real numbers, negative infinity to infinity. I would say so far, cube root is the one we use the least out of all the ones mentioned so far. And so you need to know the general shape, that it looks like a sideways squiggly. But otherwise, cube roots, you learn more about them when you actually use them. The other 5 we mentioned so far have been absolutely essential to know the shape right away. Okay, 3 more. We have a rational function. Rational in math means fraction. So it doesn't mean that you're a logical consumer. Okay, it means fraction. So 1 over x is a rational function. And that x being on bottom makes it so we're not allowed to plug in 0 to this function. Okay, so again, because there's an x on bottom, if you plug in 0, you would get 1 over 0, which is undefined. And so what happens is we get this thing called a vertical asymptote down the middle of the graph, where the graph does not use x equals 0 in its domain. So when we write the domain, we have to write it as 2 intervals, negative infinity to 0, union 0 to infinity, because again, we don't use 0 because 0 makes the graph undefined. And then rational functions also have what's called a horizontal asymptote, which is this line going sideways, where the graph also does not use y equals 0 either. So very similarly, the range is negative infinity to 0, union 0 to infinity. But one of those refers to x values, one refers to y values. So for the x's, we can't plug in 0, that's this vertical line. And for the y's, we never touch 0, that's this horizontal line. So what's happening on the left and on the right is the graph flattens out infinitely close to y equals 0, but it never actually gets there. Okay, the next one, exponential. Oh, I forgot to write the actual function here. This is y equals b to the power x, where b is a number. So this might be, for example, y equals 2 to the power x, or it might be e to the power x, where e is Euler's number. But what you need to know about this graph is that the exponent is the variable. So the letter x is the exponent. It's not on the bottom of the function. It's not the base of the function. So exponential functions have the variable in the exponent. And what's so special about them is they start off real flat and then grow exponentially once they get going. So this whole time we are multiplying the b value over and over and over again. And the more you multiply by the same number, the faster it grows. Okay, so when you hear exponential growth, you're supposed to think of this kind of curve where it's small, 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 and then it takes off really fast. Okay, the domain of an exponential function is all real numbers, negative infinity to infinity. The range, though, this thing never actually reaches y equals 0. It flattens out to the x-axis, but it never actually gets there. So our range is 0 to infinity, where we do not include the 0. So we use a parenthesis there. Okay, and then our last toolkit function is the absolute value function, denoted these vertical bars around the x. Okay, so this is absolute value of x, is how we say that. And you need to know that this is a V shape. So it almost looks like a quadratic where it's a U shape, but an absolute value is a rigid V, where you get this point at the bottom at 0, 0. The domain of this function is all real numbers. You can plug in everything from negative infinity to infinity. The range, though, just like a quadratic, is 0 to infinity, where we go down to 0, 0 at the origin, but then everything else is above the y-axis, or above the x-axis. Okay, so 0 to infinity. We go down to 0, but then we go back up. All right, so now let's learn a little bit more about specifically that absolute value function. And the way it relates to piecewise defined functions is that the absolute value function is 2 functions pieced together. And that's how we end up with that V shape. So we're going to see that in more detail here. First, a piecewise defined function is 2 or more functions that are stitched together. So I know that most of you guys have seen like TikToks where you have a stitch feature where maybe one person records a video and then someone else wants to try to copy it. So they play the original video at the beginning and they stitch their video on afterward. It's the same thing with functions. You have one function to start off with and then you stitch on another function that takes over after that. So maybe the first 10 seconds of the video are one person and then you stitch in the next minute of the video is the other person. So same thing with functions, we can stitch them together. Piecewise defined functions are still functions, which means they need to have exactly one output for every input. Okay, so remember from previous lessons, we have a definition of a function where you can only use x values once. They can't go to two different places. And the domain of each function is going to have to be defined inside the structure of our piecewise defined function. I'll show you what that one means in a second. But essentially, we have to make sure that the domain of the piecewise function makes it so that it is actually a function. Because if we use the same x values twice, then that just causes awfulness. So back to the TikTok example, imagine if when you stitch the videos together, you overlapped them. So you have both audio tracks playing at the same time. So you have the audio from the first video and the audio from the second video playing together. That would just be nonsense, and it'd sound crazy and awful, and everyone would turn it off and go to the next video right away. So with piecewise defined functions, we just have to make sure there's no overlap where one function is on top of the other function. They have to be separate. All right, so now the way this relates to absolute value of x, the graph of f of x equals absolute value x is a piecewise defined function where it's negative x on the left of 0 and positive x on the right of 0. The two graphs meet at the point 0, 0 to make the actual function. So we saw that the graph looks like a V that goes to the origin. So there's our V shape. That's what absolute value of x looks like. But let's see specifically why. So what I'm going to do is I'm going to make one side of this graph blue and the other side red, because there's actually two functions that are inside of this one function. Okay, so in order to define this, we're going to say that f of x is equal to, and the way you make a piecewise function is you put this big brace, and inside of it you write the two individual functions. Okay, so it says that on the left side it's negative x, and on the right side it's positive x. So my two functions are negative x and positive x. And those two functions meet at the point 0, 0, right in the middle of the graph. So what I want to do now is I've defined f of x as being negative x and positive x, the blue and the red one, but I need to say where each of these graphs happens. So this blue one exists only on the left side. So the x values that correspond to the left side of this graph are negative infinity, way over here, all the way to 0, right here in the middle. So I can say that the domain of negative x is negative infinity all the way to 0. Okay, so f of x equals negative x if x is negative infinity to 0. Usually, though, we have a little bit easier way. Instead of using an interval the way I just did, we can use an inequality and just say that x is less than or equal to 0. So this piece I just wrote down is the same as negative infinity to 0. Okay, so an interval and an inequality, we can use either one, but saying that x is less than or equal to 0 also means the left side of this graph, and that tends to be the easier way to write it for a piecewise defined function. For the right side of this graph, the red side, it starts at 0 and then goes to infinity, so we would say that x is greater than or equal to 0. And we just have to make sure that we don't use 0 twice. So one of these says x is less than or equal to 0. The other one says x is greater than or equal to 0. Usually, you can't have this or equal to part on both of them. But in this case, it's okay because they line up right here at 0, 0. So even though it feels like we're using 0 twice because there's an or equal to part on both, because we get the same point, it actually doesn't matter which one we use. All right, and we're going to see a little bit more in this next example. So that's the absolute value function. Absolute value of x is really two functions pieced together. And you've now seen what it looks like to write a piecewise defined function. So now we're going to write one that's not a toolkit function. Okay, so here we have a few lines that are stitched together, and we're going to write a function that represents all three of these lines. So in the future, you'll learn how to find the equations of all the toolkit functions above. But right now, we're only going to focus on linear and constant functions. So all the exponentials, quadratics, cubics, all those, you'll find out in future classes how to find the equations of those based on graphs. But for right now, we're just going to do it for lines because we've already talked a lot about lines. So it says do write, to write a piecewise defined function, we need to follow the following steps. So we're going to label each function from left to right so we know how many there are. So we want to give each of these just like, honestly, just a name. That way we know what we're talking about. I usually do this with color coding because I'm on the iPad. But for your sake, it's usually easier if you just label them as 1, 2, and 3. This is mostly just so we know what we're talking about. Okay, so when I say function 1, I'm referring to the line on the left. When I say function 2, I'm referring to the middle one. And when I say function 3, I'm referring to the right one. But we also just want to know how many there is so we can set up our function appropriately. Okay, we're going to find the domain of each of these functions using interval or inequality notation. That is the part on the side here where we're saying where x is. And then we're going to solve for the equation of each of the functions. So we want to know what the equation of this line is, this line, and this line individually. Okay, so what we're going to do is we are going to say f of x equals, and we're going to make a big squiggly brace. And inside of here, we're going to have function 1, 2, and 3. Okay, that's the basic setup. But now I'm going to rewrite it with our functions actually plugged in. So f of x is going to be equal to, and we want to say what each function is. So for function 1, we need to say the domain of this function number 1 right here. Okay, so when we look at function number 1 right there, it starts at x equals -6, and it ends at x equals -3. Where notice it's a filled in dot on both sides, so our interval will be x goes from -6 to -3, where we can write this in one of two ways. We can either write it as an inequality or an interval. So in this case, we can either say bracket -6 to -3, or if we wanted to, we could write it as an inequality, which is what I actually prefer to use. So instead of the interval there, -6 to 3, we can say x is greater than or equal to -6, but less than or equal to -3. And it's less than or equal to on both sides because the filled in dots cause us to have the or equal to part. Okay, the domain of the second function, okay, our second function goes from -3 to +2. But notice it's open dots on both sides. So it's parenthesis at -3 and parenthesis at 2, or as an inequality, we can say that this goes from -3 to 2 using less than signs. Where notice there's no or equal to part on the less than because we have open dots. So x cannot actually be -3 for this one because it's an open dot there. Instead, the first function uses the -3. All right, and then for the third line, we go from +2 to +6. Notice open dot on the left, closed dot on the right. And so we can say that that interval is from +2 with a less than, no equal to less than or equal to 6. Okay, where we put the or equal to part on the right side because we have a closed dot over there. All right, now we just need to know the equations of these lines. The easiest way to do this, we've seen how to find the equations of line using 2 points. But quite honestly, the easiest way when you have a graph like this is just continue the dots and then see where the y-intercept will be. So we can count the slope and we can find the y-intercept. So in this case, our slope is up 1, right 1, up 1, right 1, up 1, right 1. So our slope is 1. And if we continue this line, we're going to go through the point -2, 5, -1, 6, and 0, 7. So our y-intercept is going to be 7, and our slope is 1. The equation of that line is therefore x plus 7, because it's 1x because the slope of 1, and the y-intercept is 7. A constant function is easier to solve for. Okay, so the second graph, sorry, let me delete these red lines. The middle function there, function 2, is a constant function at 3. So all we do is put 3 for the equation of that. The equation of this horizontal line is y equals 3. We don't write the y equals, though, in the piecewise defined part, so we just write the 3. Okay, and then the function 3, if we continue this line, we'll see that the y-intercept is 4, and the slope of this line is right 2, down 1. So my slope is -1/2. Okay, so -1/2, where I'm going down 1/2, and my y-intercept is 4, so +4. And that's it. We found the equation of each line, we said where those lines exist, and we wrote it on the left in this piecewise defined function notation. Okay, so now for the title slide, we're going to do that, but given a situation instead of a graph. So for our title slide, we have 3 different price points at a buffet for babies, kids, and adults. So what we want to do, it says to name our function p of a. So we're going to say that p of a is equal to, and we're going to define a function here. The 3 different price points are free, which is $0, $15, and $25. So those are going to be our 3 horizontal lines that we have to represent each of these prices. They're all constant functions. And our a values where these are defined, it says it's free for babies under 2. So under 2 means from 0 to 2, where once you turn 2, you are no longer under 2. So I do not put an or equal to part on the 2, because once you turn 2, you are no longer under 2. Okay. If I want to graph that line, I would draw a horizontal line at y equals 0 and an open dot at 2. So everyone see down here, horizontal line at y equals 0, open dot at 2. Then the next price is $15, and it says that kids 12 and under are 15. So once you turn 2, you become a kid instead of an infant or a baby, and you stay a kid as long as you are not older than 12. So we include 12 because it says 12 and under, meaning 12 is included. So then what we're going to do is draw a horizontal line from 15, or at y equals 15, from 2 to 12, where we have closed dots on both sides. So notice closed dots on both sides. If you're 2 years old, you pay $15. If you're 12 years old, you pay $15. All right, and then it says adults are $25. So once you are no longer 12 years old, then you're automatically an adult. So we can either say that x is greater than 12, so just no equal sign on there, or we could start at 13. In this case, it doesn't matter, but it's better to use 12 since we ended the other one with 12. And this goes all the way up to infinity. So I don't actually put anything on the other side because it's however old you are, you're still paying $25. So once x is greater than 12, you pay $25. So once you're older than 12, you pay 25. So on my graph, I'll put an open dot at 25 for 12, and it'll go all the way off to the right where you're paying $25 for the rest of your life to eat at that buffet. So essentially, when you walk in, if you want to know how much you pay, you ask yourself, hey, how old am I? And you find out which of these 3 intervals am I in. As a 28-year-old, I am paying the $25 price. As an 11-year-old, you'd be paying the $15 price. As a 6-year-old, you'd still be paying the $15 price. As a 92-year-old, paying $25. If you're a 1-year-old, you're not paying anything, so on and so on. So a lot of things in real life are piecewise defined functions. We don't necessarily think of them that way all the time. But now that you've seen one, hopefully when you go into a restaurant that has different prices, you can break it down in your head. Like, hey, what kind of function are we actually looking at here? But again, the main thing you need to take away from this lesson is all these toolkit functions. Okay, and now if you were to go back and try this video again, you should have an answer to number 3, where hopefully you can list out all 9 of these toolkit functions. All right, see you guys next time.